All right, so the next differential operator I want to talk a little bit about is the Laplace operator. So for a scalar function f, a function of more than one variable, 2, 3, n, doesn't matter, the Laplacian of f is denoted with this capital delta triangle. So Laplacian f is equal to, and then we have the sum of the second partial derivatives of f. Okay, and so this means that you can also think of the Laplacian of a function as being the divergence of the gradient of the function, or del dot grad, of f, because that gives you the dot product with this vector right here. So when you apply the del dot like this, then you take the x partial of the first one, the y partial of the second one, the z partial of the third one, and add them up, and you get the sum of the second partial derivatives. So this guy right here, this triangle, which is sometimes denoted by this, or even more slangily as del squared, and it's the sum of the second derivatives, is the Laplace operator. And so the Laplace operator is useful for many things. So for instance, it shows up when you look at the wave equation in higher dimensions. So the wave equation looks like the second time derivative of u is equal to the Laplacian of u. And so in this case, u is a function of time and then also some space variables. So x and y if you're in a two-dimensional wave, or x, y, and z if you're a three-dimensional wave, etc. Also, the heat equation in higher dimensions. And so this is where the time derivative of u is equal to the Laplacian of u. And once again, u is a function of t and then also some number of spatial variables. And then there's also Laplace's equation. And so Laplace's equation is Laplacian of u equal to 0. And the solutions to Laplace's equation are very interesting and show up in all branches of mathematics. Solutions are called harmonic functions. And they're useful to express the solutions of other equations like wave and heat equation. You also can see, for example, suppose that you're looking at the heat equation, and suppose the solution tends to a steady state. Now this might depend on the conditions of the problem, like how much heat you're adding in or taking away or something like that. But in many cases, it's physically and mathematically realistic to assume that the heat of whatever you're modeling tends to an equilibrium, that it's like evening out, right? Well, what happens in that case? So the meaning of this steady state, that means specifically that it's no longer changing with time, right? And so if it's not changing with respect to time, the time derivative tells you how much it's changing with respect to time. So if it's not changing with respect to time, that means the time derivative went to 0. So that means that as time increases and it tends to a steady state, this equation tends to this equation, because that u sub t just disappears. Okay, and so harmonic functions, like I said, they have lots of nifty properties. So for example, if we know that u satisfies this on some region, then that implies, for example, that the maximum and minimum values, I guess I should say, for x in some region D, then the maximum and minimum value of u must occur on the boundary. It's impossible to have a local max or local min somewhere inside the boundary. Also, it's the case that the value of u, so if u is harmonic, then the value of u at any point is equal to the average value over any ball centered at x. So here B is a ball centered at x. And then you can even just look at the boundary of that ball instead and say if this is any sphere, same thing happens. And so because harmonic functions have this amazing property that they're so well balanced, they're equal to their average value over any round neighborhood, you can use this property to define what it means to be a harmonic function in some other context where maybe it doesn't make sense. So maybe, for example, you're studying graphs in the sense of graph theory, and here's a social network, right? So all these people, a line between any two people indicates that they know each other, or maybe that they're like connected on Facebook or something like that. So here's a social network, and you can use, maybe you're studying the propagation of memes through the internet or something like that. You can model that using the heat equation, and the steady state will be governed by Laplace's equation. And you can use this notion right here that the value of a function at a given point is going to be the average value of the function at all of the neighboring points to understand how that works.